Good morning, student. In the last lecture of number theory of module 1 PCC CS 404, we have discussed a theorem related to G.C.D. and the theorem is if we want to find the G.C.D of two number A and B, then the G.C.D of A comma B should be written as AU plus BV, where U and BV two integer. Application of this theorem. Now in this lecture we want to learn the in this lecture we want to learn the application of this particular theorem. Okay, so first to define a definition regarding prime integer, and according to your previous knowledge we have already mentioned that what is the definition of prime integer? If a number is divisible by itself and 1 and there hasn't except 1 is called the prime integer. But here we consider another example where we consider to define the relatively prime, which is not the meaning of the prime. It's represent a relatively prime integer. What is the meaning of relatively prime? If that doesn't mean both the numbers should be a prime number. If both the numbers should be a prime number, then nothing to prove that they should be relatively prime. But if the number it may be happen that both of these two numbers should not be the prime number, but still they are relatively prime. If it is happen that the GCD of two number is 1, then we say that these two numbers are relatively prime number. Here it's the definition of relative prime number. Two integer A and B, not both 0, are said to be a prime to each other or relatively prime if GCD of A comma B equals to 1. Okay, if its GCD is equals to 1, then we say that they are relatively prime. Here we give an example where both the number is not the prime number, but still they are prime to each other. If we consider a number, say 12, just to change the color of this, sorry, here we use this. If we integer a number, say 9, it's not a prime number because 9 is divisible by 3, and we consider another number is 20, which is also not a prime number. Okay, but the common factor of 19 and 20 is only 1, so we can write the GCD of 9 and 20, that is equals to 1. Exactly for that reason we say that 9 and 20 are the prime to each other or relatively prime number, but still 9 and 20 are not the prime number. Okay, next we move related theorem which is very important for your examination and your real life application and any other competitive examination. That is a very important theorem. You can apply this theorem in the field of number theory. It says that if the theorem says that if D is the GCD of A comma B, then A by D, it's not the symbol of dy, sir. B by D are integer prime to each other. It says that again we repeat that if the GCD of two number is D, if we divide both this number by the GCD and the remaining number, when you divide by the GCD of both the number, the remaining number should be prime to each other. Okay, so here we give an example to clear your idea. Next we move to the proof section. Say 12. Okay, 12 and another one is 18. So the GCD of 12 and 18, GCD of 12 and 18 is G C, D, 12 and 18, that is 6. Theorem says that the GCD of then the GCD of 12 by 6 12 by 6 12 by 6 and 18 by 6 that should be equals to 1, because you can easily observe 12 by 6 that is 2 and 18 by 6 that is 3, they both are the prime number, therefore their GCD should be 1. But you should not adopt the concept is that when you divide by GCD the remaining number should be a prime number. That should not be happening for every cases. Okay, so if we consider another example to the relating this term is, say we just take another example, 20. It's 20. Another one is, say, 20. Another one is, say, another number is we consider 6 into 3, say 18. Okay, if we consider this one, the GCD of 20 and 80 should be 2. The GCD is 2. That means if we divide by 2 of both the number, 20 by 2, this becomes 10, and 18 by 2, it's become 9, and their GCD becomes 1. According to this theorem, their GCD becomes 1. But this number is 10 and this number is 9, both the number are not the prime number. So you should not adopt this concept is that if their GCD, if we divide by the GCD of both the number, the remaining number should be a prime number. And the previous example says that the number becomes a prime number. This example says that the remaining number should not be a prime number, but the remaining term GCD should be 1. That's why we study this theorem, and you have to understand this theorem, what is the meaning of this theorem. Okay, so we move to the proof section. First, since D is the GCD of A comma B, therefore D should divides A. So you can write A is M into D according to the division algorithm, because D is a divisor of A. Similarly, D is again a divisor of B because D is the GCD of A comma B. Therefore, D you can write this B is N into D. It's clear for you. So A by D, that's become M. A by D, that's become M from this, and B by D, that's become N. Both are the integer. Okay, now since GCD of A comma B, if it is possible to find an integer U and V such that in the last theorem we have proved that if we express the two number GCD, you can express any two number GCD in the form of AU plus BV, where U and V are both the integers. So since D is the GCD of these two number, you should write this one is AU plus BV. Okay, since you can write this two one as AU plus BV, therefore since you can write this one as AU plus BV, so if we divide both sides by D, the remaining portion becomes A by D, B by D, A by D into U, B by D into V, and the left hand side becomes 1, it's represent that this one can be expressed as mu plus mv, where if we want to find the GCD of m and n, then you write this m and n as a linear combination of mu plus nv, which is equals to 1, which represent that the GCD of m and n should be 1, which proves that when we divide by the GCD of the number, the remaining number GCD should be 1. That means these two number should be prime to each other. Now we move to the next another proof section of this chapter. It's also very important. This one. It is also a very important theorem. If it says that if A divide by C, GCD of A comma B is 1, which represents that A should not be the divisor of B. Because if A is a divisor of B, and in that case if A and B has any other common factor other than 1, then they must cancel this common factor. But here we consider the GCD of A comma B, that should be equals to 1. If it is happened that should not be, it's the condition. If A divides BC and GCD of A comma B is 1, in that case you can say that A should divide C. A should divide C. We just make an example to clear your idea. Say 2 is a divisor of 3 into 10, 3 into 10, but 2 doesn't divide 3. 2 is not 2 and 3 has any common divisor except 1, so the GCD of A comma B should be 1, that represent that 2 should divide 10. That's why we study this theorem. Okay, exactly, that's why we study this theorem. Here it is given that now we move to the proof section. The GCD of A comma B is 1. There exists an integer u and v such that 1 can be written as AU plus BB. It is given because the GCD of A comma B is 1, therefore you can easily write this one as a linear combination of these two numbers A and B with some integer AU plus BB. If we multiply both sides by C of this equation, if we consider this one is your equation number 1, okay. So if you multiply both sides by C, then it's becomes C equals to CAU plus CBC. CBV. Since it is given that A is a divisor of BC, that means A should divide BC, this portion. A should divides this portion. Okay. Again, A should divides AU because there is a number A. So A should divide AU. Therefore, according to a previous theorem, if A divides A is a divisor of X, A is a divisor of Y, then A should be a divisor of any linear combination of X and Y. So A, according to this theorem, we can say A should be the divisor of any linear combination of AU plus BC. So here it's a linear combination. AU with multiplied with C and BC with multiplied with V. Therefore, it's a linear combination of AU plus BC. Therefore, you can say that A should be a divisor of CAU plus CBC into V, which means A should divide C. That means in this particular lecture, we just learned 2 or 3 theorem relating to the GCD, which is the real field application to find the another GCD of any combination of the number. So thank you for listening.